we have, are the following polyatomic ions polar or nonpolar? Are these polar or non-polar? Okay, so we're going to write this down briefly. So we have NO2 minus SiF4 and Cl2. Okay, so now, oh, that NO2 plus. Sorry, I have to look a little bit closer for that one. Yes, that is an NO2 plus. Okay, so with this, to find out if they're polar or non-polar, we always have to draw our Lewis dot diagram, okay? So we need to know how many electrons each offers. So nitrogen, okay, has 5 valence electrons based on it being on the 15th column, and oxygen has 6 valence electrons based on it being on the 16th column, okay? But we have a plus. When you have a plus there, that means that we have 1 less electron to work with. So instead of it being 5 plus 6 plus 6, it's going to be that, but then minus 1 at the end. So that's 12 plus 5 is 17. Minus 1, we have 16 electrons to work with. Okay, so now I'm going to put nitrogen in the middle, surrounded by the oxygens. Okay, and there we go, 1, 2. And so now nitrogen is sharing currently 2 of its 5. So 3, 4, 5. Oxygen is sharing 1 of its 6. So 2, 3, 4, 5, 6. Same thing with this oxygen. 3, 4, 5, 6. But as you remember, 1 of the electrons is gone. So I'm going to just pick this one here, because that actually allows me to do what I'm about to do, which is create new bonds, which is what's going to happen with the nitrogen and the oxygen. So instead of it being single bonds between each one, it's a double bond between each. Okay, so now that we have it like this, let's first check. We have 14 electrons. Okay, so we have 2, 4, 6, 8, 10, 12, 14, 16. I mean 16 electrons, sorry. So check, we passed that. And now we're going to make sure that we have the correct formal charge here. So nitrogen in the middle is going to be 5 valence electrons minus, has no electrons to itself and is sharing 8. So that's 5 minus 4. We have plus 1. So indeed, the positive charge here based on the NO2 plus is on the nitrogen, and the oxygen should be 0, but we'll check anyways. We have 6 minus, it has 4 to itself, and it has a bond with 4 electrons because of double bond, so that is indeed 0. So perfect. This is what we have. Now, because of this, based on the way nitrogen is, it has no lone pairs. It only has 2 types of things attached to it, which are 2 double bonds. But the hybridization for this, is sp. Okay, and we have a sp hybridization. Your form is actually linear. Now this is very important because a linear molecule means that the oxygens on each end, even though they may, actually not even may, if you look at the difference in electron activity, 3.44 versus 3.04, it's just enough to where there is, you can argue that it is technically a polar bonds between them. But even if that was the case, the molecule itself still ends up being non-polar. Why? Because it's linear and the oxygens are pulling on the middle nitrogen both the same amount of force. So overall, there's no net movement. So NO2 plus actually would be non-polar. So which atom is closest to the negative side? So the way you answer this question is if there was a part that was more negative and more positive, then you would put the atom that's close to it. So let's say, for example, for some reason, one oxygen was more negative than the other. You'd still put nitrogen because nitrogen is the one in the middle. So it's technically the one closest to the other oxygen. the oxygens are separated by nitrogen. But in this case, because it's nonpolar, we say this isn't applicable because both of them are equally quote unquote negative. Even nitrogen is the positive end because it's being pulled apart by both equally negative parts. Overall, you can't really say which atom is close to the negative side. I guess technically you could say it's nitrogen because we see that it is the positive side. That is going to be interesting. Because although the overall polarity is cancelled, the nitrogen itself is still technically the positive end. So, that's a good point. Well, I mean, no, the electrons want to be at both oxygen ends, so because they need to travel through nitrogen, it means that it also won't be positive. It will still have the same charge throughout. So with that being said, I'm going to say it's not applicable here. So now SiF4, okay, we now have to first figure out how to even form this. So silicon is actually in the 14th column, so that's 4 valence electrons, and fluorine is in the 17th column, which is 7 valence electrons. So that being said, we have in total, fluorine is 7 times 4, so that's 28, plus the 4 more, so that's 32 electrons to work with for SiS4. And what's going to happen here, we're going to put the silicon in the middle, okay, and we're going to just do that, SiF4, so that's 1 bond each. And so silicon is already sharing 4 of its 4 electrons, so that one is done. And the fluorine is now surrounding that silicon. So with this being said, we can just check quickly the formal charge. Silicon is 4 valence electrons, and it's sharing, it has 0 by itself, but it's sharing 8, so that's 0. And fluorine, doesn't matter which one, because they all have 6, and they're sharing 2, that also equals 0. So both are correct. This is going to be the real, or the theoretical Lewis structure for this. So with that being said, is this polar or non-polar? So this, because as you can see right here, each end is going to be pulling the silicon with the fluorine, and because they're all fluorines, it's going to be all canceled out because they're all equally pulling the silicon. Because fluorine is quite electronegative, it's way more than the silicon. It is definitely polar bonds, but because we have a polar bond on each of the 4 ends, overall the net movement is also going to be canceled like the NO2+. So which is the more, now which side is closer to the more negative side? This is also not applicable because the electrons will be moving throughout. Even though quote unquote is not staying in the middle that often, there's still net movement going through. I would say if anything, I'm going to put a not applicable dash for both. So this one will be nitrogen and this one will be the silicon. I'm still leaning more towards the not applicable because the electrons need to be able to move through the silicon or nitrogen to be able to get to their more negative ends. So now for the last one, Cl2. So this one is just 2 chlorines. Each one has 14 electrons, or 7 electrons, that's 14 total. And it's just going to be Cl, Cl. So this one right away, you know for sure, they're going to be non-polar because they're both the same element, so they're going to equally pull at each other. Okay? And now, for the last question, which is the atom close to the more negative side, this one is definitely not applicable. Of all the non-applicables, this one is the one that stands out the most, okay? Because these are now the same elements, so there's really going to be no negative or positive side. So I'm going to leave it like this for now. Let's see what our partner has. We have that it's a linear molecule, so although the bonds are polar, bonds will cast each other out. So the overall polarity will be 0, non-polar. This is also going to be non-polar, and this is going to be nonpolar as well. So this doesn't really answer the question of which atom is close to the negative side. So with this, I would say that it's not really applicable, but if you were to say where I guess the electrons spend the least amount of time, for at least the ones that do actually have polar bonds, you can say that one, for example, the first one will be the nitrogen, the next one will be the silicon, and then the last one, that one's definitely not applicable because it'll spend equal time in any of the chlorines. Okay, so that being said, this is correct. Going down to question number 10.